Okay, so I have to remember I upgraded my YouTube account so I can actually upload videos that are longer than 15 minutes so I don't have to stop and be all like, oh, I'm in the middle of a problem, but 15 minutes are over. No, I can be nice and slow and lazy now. So, okay. Last time I said, what is the probability of at least one head if I flip a coin twice? Well, how are the ways to get at least, no, excuse me, exactly. The ways are heads tails or tails heads. And we assumed that each of these probabilities is equal to the same thing, which is 0.25 plus 0.25, that's 0.5. So we expect exactly one head half the time. Cool. Great. Let's do another example that involves calculating, sort of looking at probabilities using data. So let's say data for the past 100 years says that today is Halloween, so that I'm recording this, so I'm just going to make this pertinent to Halloween. It says that on Halloween, the weather's been like this. Uh, uh, 32 of the past 100 Halloweens, it has there's been no precipitation, and the temperature has been above freezing. So 32 times, no precipitation, and it's been above freezing. Let's say 23 of the days, it was uh, it, it was uh, no precipitation, but it was below freezing. I think this data is, I just made this completely up, and so this doesn't really make sense, I don't think, at the end of the day, but whatever. Um, why don't I just change this right now? I'll make this 13, I'll make this 42. Okay, I like that better. And let's say 39 of the days there was precipitation, but no freezing, uh, but above freezing, and 6 of the days there was precipitation and below freezing. Precipitation. Great. Now this should all add up to 100. And just let me check for a second. 42 and 13 is 55. 39 and 6 is 45. And 45 plus 55 is 100. Great. Now I'm going to use relative frequencies to compute the probability of these events. So what is a relative frequency? So basically are ways of computing probabilities from actual data. And what it is, the probability of some event is the number of times the event happened divided by the total number of observations. Let me make that look a little bit nicer. So the total number of times the event has happened divided by, to make it look nice like this, divided by the number of observations. Okay. So that's how we get the probability, the relative frequency that This is happening. So, for example, in our case, let's let F be below freezing and P be precipitation. So we have a couple of different probabilities. So the probability that it's not freezing and no precipitation. Well, this happened 42 of the past 100 days. So it happened 42 times, and we're looking at 100 observations. So that is the probability that it's not freezing and there's no precipitation. The probability of of freezing and no precipitation is, how many times did that happen? 13. So 13 out of 100, which is 0.13. How about the probability of not freezing and precipitation? I said that happened 36 times. No, 39 times out of 100. So the probability there is 0.39. What's the probability of freezing and precipitation? I said that happened 6 out of the 100 times, so it's 0.06. Great. So that's how we can construct these. We take the number of times that the particular thing we're looking at happened, and then we divide by the total number of observations we've taken. Since we're looking over 100 years of data, and this is the number of times, say, that it was above freezing and not raining or snowing or whatever, that's how I get this probability. Again, since these numbers up here add up to 100, these numbers here will add up to 1. Okay. So now I can ask questions like, well, what is the probability that it's going to be freezing? Well, the ways that can happen is it can be freezing and, let me write it this, freezing and precipitation, or freezing and no precipitation, using sort of set notation. So P prime means not raining. So this is the probability of freezing and precipitation plus the probability of freezing and no precipitation, which is equal to freezing and precipitation was 0.06, and freezing and no precipitation was 0.13, which is 0.19. So 19% of the time we expect freezing weather. Okay. How about the probability of bad weather? What do I mean by that? Well, it's no fun to be out trick-or-treating if you still do that, although you probably shouldn't be if you're in college. But, you know, just going out on Halloween. It's not a lot of fun if it's going to be cold or rainy or both, but you know, people still do it. So what is the probability of bad weather? Well, what do I mean there? This is the probability of freezing or precipitation. Now, the ways that this can happen are it's freezing and there's precipitation, not freezing and precipitation, or freezing and not precipitation. So we put these all together. The probability of freezing and precipitation plus the probability of not freezing and precipitation plus the probability of freezing but no precipitation. This is equal to the probability of, let's see, 0.13, 0.39, and 0.06. It's 0.06 plus 0.39 plus 0.13. And this adds up, those are the right numbers, right? Those add up to 0.58. So 58% of the time we expect bad weather. Boo. Not like it goes to boo like boo hiss. I don't want this to have happened, but it did. What it is. Okay. Let's move on to another topic. Now, the first example I did above, I was talking about flipping a coin twice, and then we assigned reasonable probabilities, and we made an assumption, which is that exactly one, any way of tossing a coin twice happened the same amount of times. This is something called equally likely. So the assumption of equally likely outcomes. And this basically says any outcome has the same chance of happening. And let's just look at a couple of quick examples where we do or don't expect this to happen. For example, if I, flip a coin, heads and tails should be equally likely. If I roll 2 dice, then any possible combination of pair x, y with x and y between 6 should be equally likely. However, for example, if I'm looking at the weather, rain and no rain shouldn't be equally likely because, it probably rains maybe 30% of the time and doesn't rain, experience suggests it's usually not raining. Or going back to rolling 2 dice, any sum of the dice, any 2 sums of the dice should not be equally likely. Why not? Well, there's one way to get a 2. You have to roll 2 ones. However, there are 6 ways of getting a 7. You can get a 1 and a 6, a 2 and a 5, a 3 and a 4, a 4 and a 3, a 5 and a 2, and a 6 and a 1. These are different probabilities because possibilities 1 and 6 and 6 and 1 because we've got 2 dice and maybe the first die is a 1 and the second is a 6, or the first one is a 6 and the second one is a 1. So really these are all distinct possibilities, but this just says, okay, I should expect to get a 7 way more times than I am going to get a 2 just because there are more ways of getting a 7. So we can only apply this in cases where we think it makes sense. Okay, so now let's look at an example of computing equally likely. Well, here's the basic fact. Assuming equally likely outcomes, if E is an event in a sample space S, then the probability that E happens is 1 over the number of total outcomes. And the reason for this is that there are NS total outcomes. So if each has probability n 1 over ns, the total, the sum of the probabilities is 1 over ns plus 1 over ns plus dot 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 plus 1 over ns. This is happening ns times. So this is equal to ns times 1 over ns, which is equal to 1. So that's fine. So this is acceptable. But we want to make sure that it's also reasonable. And again, up here, I showed 2 places where it isn't reasonable, looking at rain or no rain, or rolling 2 dice and expecting a 2 or a 7, whereas flipping a coin or rolling 2 dice and just looking at the exact outcome that occurs, those should all be equally likely. I mean, in fact, that's where the games of chance basically come in. So let's look at some examples of this. In fact, I'm going to stop this video right now because although typically I just said, hey, let's let these videos get kind of long. The next one is going to be pretty long in and of itself, and I don't want you to have to search through a 30-minute long video just to find the different examples. So let's stop it right here and make one more video.